Today I'll prove the AMGM inequality, arithmetic mean of those positive numbers, A1 all the way up to AN, is greater than or equal to the geometric mean of those numbers. And we're going to use the Cauchy forward-backward method, which is a fantastic method. So here I'm going to first prove using mathematical induction when n equals 2. Let's see if I want to prove half of a1 plus a2 is greater than or equal to the square root of a1 times a2, given that a1, a2 all the way to an are greater than or equal to 0. So in that case, so is this true? I want to prove. So all I need to show is that a1 plus a2 is it greater than or equal to twice of square root of a1, a2, right? Then all I need to show is that the a1 plus a2 minus twice of square root of a1, a2 is greater than or equal to 0. Is it true? But a1 can be written as the square root of a1 square. Likewise, square root, then square. Then it's a perfect square. Perfect square. Square root of a1 minus square root of a2. Quantity squared, is it greater than or equal to 0? Obviously true. So when we're done with n equals 2. So this is the forward session. So I'm going to continue with the forward session. So I'm going to assume that. So I'm going to check if n equals to 4, what's going to happen, right? So over 4, a1 plus a2 plus a3 plus a4. Right? Is it greater than or equal to the fourth root of multiplied together, right? So, but then I can just rewrite it into half of a1 plus a2 plus half of a3 plus a4. Okay? Then I can use when n equals 2, I'm going to treat this and that as an individual entity, right? So half of them greater than or equal to the square root of this times that. Right? Half of a1 plus a2 times half of a3 plus a4. But then I can use again when n equals 2, right? I've achieved my result. Greater than or equal to the square root of a1 times a2 times square root of a3 times a4. So that is exactly the fourth root of a1, a2, a3, a4 multiplied together. All right, so this is good. So then I want to say that, okay, let's assume that when n equals, so generally speaking, 2, 4, 8, 16. So I'm going to assume when n equals 2 to the power of k, it's true. Assuming it's true, in other words, 2 to the power of k, right, over an a1 all the way up to a sub 2 to the power of k is greater than or equal to the 2 to the power of kth root of a1, a2 multiply all the way up to a to the power of a sub 2 to the power of k. Now, I want to check n equals 2 to the power of k plus 1, what's going to happen? Is it still true? So when n equals 2 to the power of k plus 1, I have this many. So 2 to the power of k plus 1, a1 all the way, a to a sub 2 to the power of k plus 1. Right? But then I can rewrite it into half of 2 to the power of k at the bottom, a1 plus all the way up to a sub 2 to the power of k plus the other half is 2 to the power of k at the bottom. Next one is a sub 2 to the power k plus 1 plus all the way up to a to the power of 2 to the power of k plus 1. Right, so this plus 1 and that plus 1 are different. This plus 1 is after 2 to the power of k, or 2 to the power of k as a whole entity. But this one follows right after k. So I have exactly 2 to the power of k many members in here. In total, I have 2 to the power of k plus 1 many members in here. So after this many members, I still have exactly the same many members as here, right? From this member all the way up to this member, 2 to the power of k many of them. Right, altogether, I have 2 times 2 to the power of k many of them. So in this case, I have, when n equals to 2, half of this number plus this number, right? N equals 2, that case, greater than or equal to the square root of this times that. Right? So 2 to the power of k, a1, all the way, a 2 to the k times 2 to the k, a 2 to the power of k plus 1 plus all the way a to the power of 2k plus 1. Okay. So now I can just use when n equals 2 to the power of k, right? Assuming this is true. So assuming that is true, I have exactly greater than or equal to the square root of. So this is greater than or equal to the 2 to the power of k through a1 multiply all the way a to the a power 2k times, again, this is the same, 2 to the power of k, a 2k 1 times all the way a 2k plus 1. Right, multiply everything together. So this is equal to, so this is 2 to the power of k root, that's the power of 1 over 2 to the power of k. So outside here, square root 1 over 2. So 1 over 2 to the power of k plus 1. So that's the 2 to the power of k plus 1 root of a1 multiply all the way to a 2 to the k plus 1, right? So this is exactly when n equals 2 to the k plus 1. Exactly, I have geometric mean, right? Arithmetic mean, geometric mean. Right? So this is the forward section. What I've just done is I've proven that when n equals 2, it's true. When n equals 2 to the power of k, it's true. And also, assuming when n equals to, then I've proven n equals 2 to the power of k plus 1 is also true. So a mathematical induction I automatically reached when every time I have the form of 2 to the power of n, then my proposition is true. Right, so this form. So this is the forward section, right? N can go on forever. I can become infinitely large. So the backward section. So inverse mathematical induction. So we assume when n equals k is true, right? Generally speaking, a mathematical induction, we want to prove n equals k plus 1 is true, but this time I want to prove n equals k minus 1 is true. It's an inverse mathematical induction. Right? So in other words, when n equals k is true, so a1 ak over k greater than or equal to the kth root of a1 plus multiply all the way ak. This is my assumption. So I want to prove this, right? So I want to prove k minus 1, a1 plus all the way a k minus 1. Is it greater than or equal to k minus 1th root, right? So before that, I want to rewrite it into 1 over k. Of course, multiply by k, right? Still the same thing. K minus 1. Sum I goes from 1 to k minus 1 ai. Now, this time first, let me just rewrite it into 1 over k. And top is k, but k minus 1 plus 1 still the same thing, right? And k minus 1. Sum I from 1 to k minus 1 ai, right? So this fraction, right, so it can be separated into k minus 1 over k minus 1, that's 1. 1 over k minus 1, right? K minus ai. Right. Then we can distribute this, right? 1 onto this, 1 over k minus 1 onto this, right? 1 over k, bracket, sum, right? The same sum, ai, distribute this onto that, plus 1 over k minus 1, sum, ai, right? And now I can say that how many members, k minus 1 members, and I treat this as a whole entity. So I have k many numbers, right? K many of them over k. So that's when n equals k. I assume n equals k is true, right? Using my assumption. Automatically greater than or equal to the kth root of. Here is the a1 plus all the way up to ak minus 1. So I just multiply a1, a2, all the way ak minus 1. Also multiply by this whole thing, right? 1 over k minus 1 sigma I 1 k minus 1 ai. Right, this is a multiplication. Now, then I can just raise both sides to the power of k. Right, so I mean this side and that side, right? So I can say that left-hand side, k minus 1 to the power of k, sigma I from 1 to k minus 1, ai quantity to the power of k greater than or equal to, so this k's root will be gone. a1, a2, all the way multiply to a k minus 1 times 1 over k minus 1 times sum I from 1 to k minus 1 ai, right? So we're going to treat the sum as a whole entity, right? Simplify this out. As a whole entity, power reduced by 1, right? This, so k minus 1 simplify with this k minus 1. So power will reduce by 1 again. Right, so these are all gone, becomes 1. So what do I have now? I just take the k minus 1th root on both sides to just cancel these ones out, right? So I have sigma I from 1 to k minus 1 ai over k minus 1 greater than or equal to the k minus 1th root of a1, a2 multiply all the way ak minus 1. Right, so what is this? So this is when n equals k minus 1, right? Exactly the arithmetic mean of those k minus 1 many members, right? Greater than or equal to the k minus 1th root, right? So I've really proven this is true, right? Assuming that n equals k is true. So this is the inverse mathematical induction, right? So this is the, I think, most fabulous part of this whole method, right? The backward section is this section, right? So what I've done, so first of all, we've proven that as long as it's this form, right, we have this many members, 2 to the power of n, this many members, and go on forever, right? Positive integer go on forever, always true. Right, then we prove as long as n equals k is true, then n equals k minus 1 is also true. For example, k is equal to 100, then also inequality is also true if we have 99 numbers. Right, but if it's true for 99 numbers, then it's also true if we have 98 numbers, 97 numbers, and so on and so forth, all the way down to 2. Right? They're all true. So that's essentially telling us that no matter what n is, right, any positive integer, right, it's always true. Always true. If you ask, is it true for 100 million? I say it's always true. Right? 100 million, because 2 to the power of n can go on forever. Can be bigger than anything. Right? Can be bigger than anything. Then we use inverse mathematical induction, reduced all the way down. Right? Right? If it's true for 100 million, then it's true for any number, all the numbers in between 2 and 100 million, right? They're all true. Right? This is inequality. 100 trillion, right? 100 trillion is also true. Then using, according to our inverse mathematical induction, right? 1, 2, 3, 4, all the way up to 100 trillion. They're all true, right? So no matter what n is, right? They're always true.